Hello, it's Keith here and this is lesson 15 of the multi-platform series of my Z80 programming tutorials. We're going to be looking at the software Tilemap code. You can see it scrolling away all over the place here. And today we're going to be discussing something known as the SuperTile map. What's the SuperTile map? Well, first of all, let's discuss the problem we're going to have with making our scrolling game. Now, let's pretend we want to make a game and we want to have a nice big world map. Let's say it's going to be 256 tiles wide and 256 tiles tall for a nice big New Zealand story type game where we can sort of jump up on platforms in a X and Y axis. So nice big multi-directional tile map. Well, 256 times 256 is 65535, 64 kilobytes. Well, if our tiles are 1 byte each, then 256 times 256 would be 65535, and that's the entire memory of our 64K system. So maybe we need to rethink how we're going to do things. Well, what we can do is we can compress it in some way. And if we look at this game, if I press the right key here, you'll see this game is basically designed in 4x4 squares of tiles here. You can see there's a block of tiles here and a block of tiles here. And what we do is we define blocks of tiles in 4x4 areas, and we define those as a super tile, and then we define our game level in super tiles. So instead of using 1 byte per tile, we're now using 1 byte every 4 tiles, excluding the definitions of the super tiles, that is, and that allows us to have a very huge game map, provided it's made up of repeating 4x4 tile patterns, and hopefully it will be, otherwise it won't work. So that's what we're going to be looking at today. We're going to be looking at the code that converts the super tile map, which is the game world, into the logical tile map, which is the data that the drawing routines use to get the graphics quickly on the screen. We looked at those last time. So the SuperTile map is effectively saving us some space. We're also going to look at the code that handles the partial scrolling. Now, our logical tile map is bigger than our screen, and it's coincidentally or not, one SuperTile bigger than the visible screen. So there's equivalent of 4 hidden tiles on the left, 4 hidden tiles on the right, 4 hidden tiles on the top, and 4 hidden tiles on the bottom. And that's so that as we scroll, we can start to see partial new data. But then once we scroll over the last super tile in the logical tile map, we jump back to the middle and we recalculate the entire logical tile map for that new position. So we've got a logical position within our game world. The logical tile map is filled from the super tile map based on that logical position, and then the code that we've seen before will draw that logical tile map to the screen accordingly. So that's what we're going to be looking at today. It's all a bit tricky, I know, but I'm afraid that's what this is like. This is a complex subject. There's no magical trick to doing this easily, I'm afraid, so that's what we've got to deal with. So that's what we're going to be looking at. So let's get the old Sam Coupe example out the way here, and let's go over to our code and let's start looking at it. Okay, so the example we're looking at today is defined with a 16 by 16 super tile map. Now there's a little bit of extra space here. This is basically some dummy data, which is just so that as we're scrolling down, we can see parts of the top again before we wrap around. Now, the tile map isn't infinite here, so you will see as the demo runs, occasionally it will get to the bottom and then jump back to the top. As it scrolls too far to the right, it will just continue on. Now, unlike the logical tile map, which is organized vertically, the super tile map is organized horizontally. So this is the top left super tile, and this byte here is the next one across, and this byte here is the next one across, and this is the second line. Now each of these definitions here will be 4x4 tiles. So it's a super tile, which means it contains multiple tiles, and as I say, the example we're looking at today is programmed to work in 4x4 super tiles. So 3 here defines SuperTile definition 3, 1 here defines SuperTile definition 1, 0 here defines SuperTile definition 0. Now I've actually got 2 SuperTile maps here, and this is because this example can actually work with parallax and have multiple layers. It is slow. Now you can see we've got the background with all the nice graphics, and then we've got this semi-transparent solid filled area above it, and they're essentially moving as 2 separate layers, and they've been calculated as 2 separate ones, and then they're being drawn to the screen here. So in theory, it can do this, and that's why the example code we're looking at today has 2 separate super tile maps here. Now, this is the background one with the graphical tiles, and this is a much simpler foreground layer with solid fill and empty tiles here. So basically, this is the top row of the SuperTile map. As I say, it goes across, and then this is the second line, and each of these is in 4x4 blocks of tiles. Now the tile definitions are here, and these are in the same format as the logical screen, so 2 bytes per tile, and they will point to the data that is being used to fill the tile, and there are some offsets being added, and these are to define the bitmap tiles and the solid fill tiles and things like that. So it's a little bit of a tricky format here. Now if I was going to use this in actual game code, which I'm afraid I don't have plans to do at the moment because I don't have time to write such a complex game, but if I was going to, I would actually write some kind of editor, probably in C# to do all of these definitions for me. I did do some testing with a previous version of this code, and that's what I did to make it usable. But you know, for the example we're working with today, we've sort of hand cranked it, so to speak. So we're defining each of the tiles in logical format here that make up the SuperTile. You can see there's 1, 2, 3, 4 here, and 1, 2, 3, 4 here, because as I say, a SuperTile is 4x4 logical tiles. So there we go. Now, when it comes to actually drawing the tile map to screen, we have a virtual offset for X and an offset for Y. Now, this is used to do all of the calculations. It's used to calculate the position within the SuperTile map that is used to define the logical tile map, and then it's used to define the whole tile scrolling. You know, what is the top left tile? You know, is it 0, 0, 1, 1, 2, 2, etc. And it's also used to define the partial scroll. Now, if I just go over here to the graphical example here, we've got a nice colored example here. Now the tile map is only 16 tiles wide, the SuperTile map, so we're only using 1 byte of the 2 byte part, but this is sort of designed that it would probably be much bigger. You'd probably want a game world much bigger than 16 SuperTiles wide, but as I say, the example we're using today, the top byte, isn't used, but the remaining bits of the bottom byte are split up, as you can see here. Now the current offset in the SuperTile map for X and Y is defined by the top 4 bits here. The whole tile offset within the SuperTile, as I say, there's one hidden SuperTile on every side of the screen, and so we will be scrolling into the SuperTile on the left or into the SuperTile on the right, or the top or the bottom, and that offset is defined by O here, these 2 bits here. And then within a tile, not a SuperTile but a tile, we can actually do, in some cases, half and quarter scrolling. That depends on the system. The Spectrum can only do full tiles, the CPC can do half tiles, and the Samcoupe can do quarter tile scrolling. It just depends on the technical abilities of the system with regards to the layout of the screen. So we've got 2 bits that will define that half or quarter scroll where applicable, and on the systems that can't do it, they'll simply be ignored. So we've got our bits here that define our position within the SuperTile world for the drawing. Now, if we go back to our code here, we've got 2 versions. We've got the live version here, and this is used for the current position. But then we've got a second copy here, and this is the position that has been calculated to use to fill the logical tile map. You see, as long as the position within the SuperTile map hasn't changed, it's just a partial scroll within those hidden tiles that we've done, then we don't need to recalculate the logical tile map from the SuperTile map. But when the SuperTile map position has changed, we need to recalculate everything. And so this is a backup of these so that we can work out when things have changed, and that's what we will be doing. Now, when it comes to drawing the tile map, we use calculate and draw tile map here. We need to specify the SuperTile map in IX, the data that defines our position. That's what we just saw just here. It's in different places on different systems because of the ROM problem with regards to things like the Sega Master System. And the tile buffer, which is the logical tile map, where we're going to write the data to actually show to the screen. Because remember, the drawing routines use the native format, which is the memory addresses of the bitmap data for speed, but the SuperTile map is compressed for efficiency because we can't store everything in raw format. Because as I say, 256 by 256 at 1 byte would be 64K, our entire system memory, and actually we're using 2 bytes per tile, so we wouldn't even be able to do that. So that's why we're doing it. Now, the routine that does all the work is calculate and draw tile map, which is just here. So this will do all of the work of working out the contents of the SuperTile map, and then once it's done that, it will use the drawing routine that we looked at last time, which actually gets the logical tile map onto the screen. Now, the first thing we're doing here is we are loading in the current position within the SuperTile map, and we're comparing the top 4 bits to the position that we drew last time. And the reason we're doing that is because the top 4 bits are the SuperTile map position. Remember, these bits are used to calculate the position within the logical tile map, and as long as these 4 bits or even more if we were using 16 bits. These bits haven't changed. The SuperTile map doesn't need to be recalculated, so we can just use the same one as before. So that saves some time, of course. So we're just skipping over to here, all the way down to here. And if we're just going to draw what we had last time, if these bits haven't changed. But if they have changed, we're going to need to refill the logical tile map from the SuperTile map. And that's what we're going to do just here. Now, we're going to use the stack pointer for reading. We're misusing the stack. We're going to be reading in those SuperTiles quickly to save us some speed here. So what we're doing here is we're backing up the stack pointer, and we're not going to be able to use the stack for anything from here onwards, not anything normal like a call. We're going to be using it for reading. So what we're doing next is we are calculating the Y offset within the SuperTile map. That's these bits here. You can see we're using IX offsets here for the position within the tile map, and that's so we can point to some kind of RAM offset, and this allows us to use multiple tile maps if we're doing parallax layers. Again, I'm not really suggesting this is a good idea because of speed, but I wanted to make the code as flexible as possible, so we are able to use multiple offsets to multiple data sources if we require. Okay, so here we are now loading in our Y position here. Now our tile map is 16 tiles wide, and coincidentally, because we're using the top 4 bits here as our Y position, that is effectively a multiple of 16. So we're just loading it straight into BC here, and we're adding it to IX to calculate the Y offset within the SuperTile map. We're then doing the same for the X position here. Well, this is the X position, but we need to shift it quite a lot. So we're shifting it all the way over here. We're shifting, and you can see we're doing B as well, but B is actually unused in this example because, as I say, the format we're using is just a 16 tile wide tile map. If we were using a much bigger one, you would want to start to bring B into play, but it's not in this case. So we're shifting that to the right, and then we're adding that to IX as well. So IX now contains the position within the SuperTile map of the first SuperTile that we need to copy to the logical tile map. Now here we are getting back the logical tile map address. We've backed up the stack pointer before, but it will still be pointing to the correct data. So when we do this, we will get back the logical tile map address that we backed up originally here. And then what we're doing here is we are calculating the logical tile map height in SuperTiles, because divided by 4, and we are then backing up DE using a memory address here. We're going to restore this later on either via self-modifying code or a memory address, just depending on if we're using ROM with regards to the Sega Master System or RAM. Again, as I say, we can't use the stack pointer at this point because as soon as we've loaded the stack pointer here, POPs will actually read data from the SuperTile definitions and not from the actual stack. So that's what we're doing there. Okay. So what we're doing next is we are going to read in a SuperTile number from the calculated position within the SuperTile map, and we're then going to use that to calculate a position within the SuperTile map definitions. And so we're doing that here. Each SuperTile definition uses 16 tiles, 4x4, and each tile is 2 bytes. So we're multiplying that up here. We're adding that to the SuperTile definitions base here, and we're then loading the position into HL within the SuperTile definitions of the SuperTile we want to transfer. We're then transferring that address to the stack pointer, and we're going to basically pop bytes out of the SuperTile definition, and popping a pair of bytes will effectively be 1 tile, and that's what we're going to do. So we're popping a tile out of the SuperTile map here, we're loading it into the logical tile map, which is the ones we're going to show to the screen later, and we're doing another one here, and so we've done 4 logical tiles here into the logical tile map. So these will be transferred down the screen like that. Now once we've done 4 consecutive vertical tiles within the logical tile map, we need to jump back to the top, and so the way we do that is we basically have got BC primed here, and so this is the amount we need to add to our current position within the logical tile map to move to the start of the next column to continue filling. So that's what we're adding here, and then we're going to repeat using A as the counter here. We're doing 4 columns basically, so we're doing that, and that will copy a SuperTile into the logical tile map. Now once we've done that, we're then restoring the logical tile map position here. We've now effectively done an entire horizontal strip of the SuperTile map converted to the logical tile map. So we're now going to move down the SuperTile map, and we're going to do the next one, and that's what we're doing here. and we're then going to carry on and repeat and do the next row. So we jump all the way back up here and we read in more supertiles and we transfer more supertiles to the logical tile map. And so once all of this completes, it's a bit of a struggle, I know, we then restore the stack pointer, and at this point our logical tile map has the correct data to show the current position within the SuperTile map. What we're doing next is we're getting the tile offset with these bits here, and this is the position that we need to offset vertically within the logical tile map, and that defines the first tile we need to show in the corner of the screen. Now the logical tile map is organized vertically, so we just need to add that position times 2, because there's 2 bytes per tile, to calculate the offset for the first one vertically. Horizontally, we need to multiply it effectively up quite a lot here, so we're shifting to the left here, and that's because the logical tile map is 32 tiles wide and each tile is 2 bytes, so we're effectively multiplying by 64 here, and then we are adding that again to the offset here. And DE now contains the whole tile offset within the logical tile map of what we want to show. Now the only remaining thing to do is take the half and quarter shift bits here, which are the partial offset of a tile for the smooth scrolling, and we're loading the bottom 2 bits into A, and we also load C with the Y shift as well. Now on the Amstrad CPC, there were 2 versions of the code because of the screen coordinates. The layout of the screen coordinates is a bit tricky for vertical movement, so there's actually 2 versions, one to do the normal tile position and one to do a half tile shift. That's why we can't do quarter tile shifts on the CPC. We'd have to have 4 versions, which I didn't think was worth it. Now, so we're comparing bit 1 of C here, but in some cases the tile map code will be more detailed like the Sam Coupe version, and we'll use more bits of C as well, but in some cases they won't. The X offset is done differently. We can usually, in most systems, just do a memory offset within the VRAM and calculate our shift in that way, and that's what we do on the CPC and the Sam Coupe. So we're taking the 2 bits there and we're masking them off here so that the code can immediately use that, but C may or may not be used just depending on the system. Anyway, it's a bit of a pain, I know, but that's what it takes to get this working on these systems. Anyway, there we go. That's all we're going to be looking at today. I think we've got another lesson to come back to later on, in which we're going to be discussing the sprites, because we have sprite code as well, which uses the tile map as well. So we're going to have to come back and have a word about that in a future lesson. But that's what we'll be covering today. If you've liked what you've seen, please like and subscribe. If you like the videos, YouTube will recommend them to more people. And if you subscribe, it encourages me to make more videos, because it takes an awful lot of time to keep making videos, and especially on more and more obscure topics like this. It's a lot of work. It's quite hard. So it would really help me out. Anyway, I hope you found some interest in this. I hope it's been useful to you in some way. You can get the source code from my website and do whatever you want with it. Anyway, whatever you do, I hope you have a lot of fun with your Z80 programming. Thanks for watching today, and goodbye.